The ocean's surface, a vast expanse of blue, is rarely at rest. Waves, driven by the wind, roll and crash onto the shore in an endless cycle of motion and energy. This mesmerizing dance of the waves, a symphony of nature, captivates our senses and invites us to ponder the forces that shape our world. Waves are more than just water in motion. They are carriers of energy. As the wind blows over the ocean's surface, it transfers some of its energy to the water, creating ripples that grow into waves. The size and strength of a wave depend on the wind's speed, the distance it travels, and the depth of the water. As waves approach the shore, the shallowing seabed interferes with their movement, causing them to slow down and bunch up. This process, known as shoaling, forces the wave's energy upward, resulting in the dramatic crests and troughs we see crashing on the beach. Imagine trying to pinpoint the exact location of a wave as it travels across the ocean. The wave is not a solid object but a disturbance in the water, constantly changing shape and position. We can talk about the wave's general location, but defining its precise position becomes a futile exercise. This inherent uncertainty is not limited to ocean waves. It extends to the very fabric of the universe, to the realm of atoms and subatomic particles. Just as a wave is a disturbance in water, particles, like electrons, exhibit wave-like behavior, blurring the lines between waves and particles. This wave-particle duality, a cornerstone of quantum mechanics, challenges our classical understanding of the world. In the quantum realm, particles do not follow predictable paths like billiard balls on a table, but exist as probabilities, their properties smeared out like waves. At the heart of this quantum fuzziness lies Heisenberg's uncertainty principle, a fundamental concept that governs the behavior of particles at the atomic and subatomic levels. This principle, named after the German physicist Werner Heisenberg, states that we cannot simultaneously know both the position and momentum of a particle with absolute certainty. The more precisely we try to measure a particle's position, the less certain we become about its momentum, and vice versa. This trade-off, this inherent uncertainty, is not a limitation of our measuring instruments but a fundamental property of the quantum world. This principle can be understood by considering the act of measurement itself. To observe an electron, we need to shine light on it. However, light, composed of photons, carries energy and momentum. When a photon interacts with an electron, it alters the electron's momentum, making it impossible to determine both its position and momentum with perfect accuracy. Section 4. The interplay of waves and particles. A unified view. The wave-particle duality and Heisenberg's uncertainty principle force us to abandon our classical intuitions and embrace a new way of understanding the universe. We must accept that particles do not exist in well-defined states but as probabilities, their properties described by wave functions that evolve over time. These wave functions, like the waves on the ocean's surface, spread out and interfere with each other, creating patterns of constructive and destructive interference. These interference patterns determine the probability of finding a particle at a particular location. The act of measurement, of observing a particle, collapses this wave function, forcing the particle into a definite state. However, until measured, the particle exists in a superposition of states, a blend of possibilities, like a wave spread out over a vast expanse. Section 5. Embracing the unknown, the allure of quantum mechanics. Quantum mechanics, with its counterintuitive concepts, challenges our perception of reality. It tells us that the universe is not a clockwork mechanism governed by deterministic laws, but a realm of probabilities, where chance and uncertainty reign. This inherent randomness, far from being a nuisance, is the engine of creation, the source of the universe's diversity and complexity. It is through quantum fluctuations, random bursts of energy from the vacuum, that particles can pop into existence, creating the stars, galaxies, and ultimately ourselves. The uncertainty at the heart of quantum mechanics is not a sign of our ignorance but a testament to the richness and strangeness of the universe we inhabit. It is a reminder that the more we delve into the nature of reality, the more we realize how much remains unknown, how much there is still to discover. Section 6. Beyond the shore, the universal significance of uncertainty. The lessons learned from the ocean's waves and the quantum world extend far beyond the realm of physics. They teach us to embrace uncertainty, to find beauty in the unknown, and to approach the world with a sense of wonder and curiosity. Just as a wave's journey is shaped by the wind and the ocean floor, our lives are shaped by countless factors, many beyond our control. Embracing this uncertainty, accepting that the future is not predetermined, allows us to live more fully in the present moment. The interconnectedness of all things, from the smallest particles to the largest galaxies, reminds us that we are part of something much larger than ourselves. By embracing the unknown, by asking questions and seeking answers, we contribute to the ongoing story of the universe, a story written in the language of waves, particles, and the enduring mystery of existence.